We live in a world built out of, well, stuff, right? Buildings, phones, cars, all held together by materials. Most of us probably don't give a second thought to.
Exactly. But what if you could peek behind that curtain?
Yeah, that's what this deep dive's all about. We're tackling metallurgy for the non-metallurgist to kind of unlock the science behind the metals shaping our lives.
Think of it as your backstage pass, maybe. Understanding what makes things strong or bendy or,
Yeah.
why they sometimes rust.
And we've got Harry Chandler's handbook here. It's like designed to make metallurgy understandable for everyone, not just the specialists.
Yeah, it really is. And it's packed with these great stories, from how alloys were first kind of stumbled upon to the big decisions engineers make choosing materials.
And why things sometimes break down when they shouldn't.
Exactly.
So our job today, we're going to sift through this handbook, pull out the most mind-blowing bits, those aha moments that give you a real feel for metals and alloys without, drowning you in jargon.
We're definitely aiming for those surprising facts and clear explanations that'll stick with you.
Okay, so ready to jump in? Because our first story, it actually starts with a complete accident.
That's right, yeah. Chapter 1 takes us to the accidental birth of a no-name alloy. So picture this. It's 1906. There's this German metallurgist, Dr. Alfred Wilm.
Okay.
And he's working for the Russian government. They need something tougher for their artillery cartridge cases. Pure aluminum is light, which is good.
But too soft.
Way too soft for that kind of job.
Yeah.
So Wilm starts experimenting. He's mixing aluminum with about 4% copper and just a tiny bit of magnesium, maybe 0.5%.
Right, so he's making an alloy. Now, they knew about heating and cooling metals back then, didn't they?
Oh, yeah, heat treatment wasn't new. But the thing was, whatever Wilm tried initially, the standard heating and cooling methods, well, they just weren't giving him the hardness he needed. But here's where it gets interesting. Kind of weird, really. It involves him being away from the lab for a weekend.
Okay, what happened?
Well, he did the standard thing first. He quenched his sample alloy in water, cooled it down really fast.
Right.
But then he left it, just sitting there at room temperature for a few days, apparently over the weekend when he wasn't around.
Just left it.
Yeah. And when he came back, guess what? It was way harder and stronger, significantly so. This, unplanned pause. It accidentally revealed a whole new way some alloys could gain strength.
Wow. So this waiting period, the aging.
Yeah.
That wasn't a known technique at the time.
Not like this. No, not at room temperature, not unintentionally. The hardening that happened, it was completely unexpected based on the heat treatments they were using. It was a totally new phenomenon.
That's amazing.
And by 1909, this accidental discovery, this alloy that didn't really even have a proper name yet, it gets patented as Duralumin by a German company. Duraner Metallwerk?
Duralumin. Okay, I've heard of that. But it wasn't cheap, was it? I think I read somewhere it was way more expensive than just plain aluminum.
Oh, massively more expensive. You're absolutely right. Initially, Duralumin cost something like $440 per kilogram.
Wow. Compared to what? For pure aluminum?
Well, the projected cost for pure aluminum then was around $24 per kilogram. So yeah, a huge jump. It really showed how special and, frankly, how much better its properties were.
But even with that price tag, people must have seen the potential immediately. It started getting used in some pretty groundbreaking stuff, didn't it?
It absolutely did. Duralumin was a real game changer for what they called the age of innovation back then, early 20th century. You think about the Wright Flyer.
Yeah.
Sure, it had cloth wings and stuff, but some key engine parts, they really benefited from Duralumin's amazing strength compared to its weight.
Okay, engine parts on the Wright Flyer. What else?
Count von Zeppelin's airships. Those huge, rigid airships like the LZ-6, the LZ-7 Deutschland, the LZ-8, they relied heavily on this new, lightweight, and strong alloy for their structure.
Airships. That's incredible. What about things on the ground? Cars.
Yep, the auto industry was booming, and they saw the potential too. Duralumin started showing up in racing car parts, things like connecting rods, crankshafts. Anywhere shaving off weight without losing strength gave you a massive performance edge.
So that whole decade, 1900 to 1910, was just buzzing with this stuff.
Totally. A real hotbed for metallurgy, driven by the needs of planes and cars.
Okay, so this accidental discovery really sparked something huge. But the mystery. How did it actually get harder just sitting there? What was going on inside the metal? That brings us to Chapter 2, right? Dr. Wilm's mystery. What happened?
It does. And to get that, we need to zoom right in down to the atomic level. The basic building blocks, atoms.
Okay, atoms, nucleus, electrons orbiting.
Right, protons, neutrons in the middle, electrons whizzing around. Now, in solid metals, these atoms aren't just, a random pile. They line up in really specific repeating 3D patterns. We call them space lattices.
Like a perfect tiny crystal structure.
Exactly. Think of it like stacking identical blocks perfectly over and over. And within a piece of metal, you have these individual crystals. They're called grains.
Grains.
Yeah, and where these grains meet, those are the grain boundaries. Imagine a mosaic tile floor. Each tile is a grain. The grout lines are the boundaries. And these boundaries, they really matter for the metal's properties. They can sort of get in the way of things moving through the metal.
Okay, so ordered atoms, grains, boundaries. Where do the extra atoms, like the copper and magnesium and duralumin, fit in?
Ah, good question. That's where we get solid solutions. When you mix metals, the atoms of the added elements, the solute atoms, they have to go somewhere in the main metal structure, the host lattice.
Right.
There are basically two ways. If the atoms are roughly the same size, the solute atoms can just swap places with some of the host atoms. That's called a substitutional solution.
Like swapping a red brick for a blue brick in your stack.
Perfect analogy, yeah. The other way is if the solute atoms are much smaller, then they can kind of squeeze into the gaps between the host atoms. That's an interstitial solution, like putting tiny beads in the spaces between your Lego bricks.
Got it. And how much can dissolve? That depends on things, like temperature.
Exactly. That's solubility. Just like sugar dissolving in hot tea versus cold tea, temperature has a huge effect on how much of one metal can dissolve in another.
Okay, so back to Wilm's experiment. He heated it up first.
Right. That initial heating, the solution heat treating, allowed more copper and magnesium to dissolve into the aluminum than would normally be possible at room temperature. He created a supersaturated solution.
Holding more than it should.
Sort of, yeah. Then the quick cooling, the quench, it kind of freezes those atoms in place, traps them within that aluminum lattice.
Okay.
Then comes the key part, diffusion. That's just the natural tendency of atoms to move around within a solid. It happens all the time, even at room temperature, just really slowly.
So the heating got everything mixed up, the cooling crapped it, and then the waiting. The waiting let those trapped atoms start moving around again, but slowly.
Precisely. That waiting period, the natural aging, was crucial for duralumin. It's what allowed the hardening to happen.
And how did that movement make it harder? That still seems a bit backward.
It does, yeah. But it's because of something called precipitation hardening, or age hardening. During that aging time at room temperature, those dissolved copper and magnesium atoms, they don't just wander randomly, they start to slowly clump together, forming incredibly tiny particles. We call them precipitates, scattered throughout the aluminum structure.
Tiny clumps, like little roadblocks?
Exactly like roadblocks. See, metals deform because defects in their crystal structure, called dislocations, can move. Think of a wrinkle moving across a carpet.
Okay.
These tiny precipitates get in the way of those dislocations moving. They obstruct that slippage. The more of these tiny obstacles you have evenly spread out, the harder it is for the dislocations to move, and so the harder and stronger the metal becomes.
Ah. So that's what happened over Wilm's weekend. He accidentally created the perfect conditions for these microscopic roadblocks to form.
He really did, an unintentional masterpiece of material science.
That is a fantastic story. It really shows how discovery can happen. Okay, let's shift gears a bit. From that accidental wonder, let's talk about the real workhorses. Steels and cast irons. Chapter 3 gets into why they're used where they are.
Right. Steel, fundamentally, it's iron mixed with carbon. And it's amazing how just a tiny amount of carbon drastically changes the properties.
How much are we talking?
Well, we classify steels based on carbon content. You have low carbon steels, medium carbon, high carbon. And then you get into tool steels, which have even more. Each step up in carbon generally makes it harder, but maybe less bendy.
Right, so it's not just about hardness. There are other things engineers care about, like how much it stretches before breaking or how it handles being hit suddenly.
Absolutely. Chapter 3 covers these mechanical properties. There's strength, obviously resisting stress. Ductility, that's the ability to deform, stretch, draw into a wire without snapping. Hardness, resisting scratches, dents. Fatigue resistance, handling repeated stress cycles. And impact resistance, taking a sudden blow.
Wow, okay. Lots to consider. And how do they measure all that?
They have specific tests, like tensile testing, where they pull a sample until it breaks, measures strength and ductility. Hardness testing involves pressing a standardized hard point into the surface, things like that.
Makes sense.
Yeah.
Now, steel production. We pictured giant factories, sparks flying. How does it go from, like, iron ore in the ground to a steel beam.
Yeah, the book has a great flow diagram for that. It starts with getting iron from the ore, usually in a blast furnace. Then you refine it, get rid of impurities, control the carbon content. This happens in different kinds of furnaces, older open hearth ones or more modern electric arc or induction furnaces.
Okay, so you melt it down, purify it.
Right. And then the molten steel is cast into these intermediate shapes, big blocks called blooms or billets, or flat pieces called slabs. These are then processed further in mills.
Into the final shapes we recognize.
Exactly. They get rolled into bars, rods, wire, sheet metal, or those big I-beams and other structural shapes for construction. It's a whole process.
Sounds intense.
Yeah.
You also mentioned cast irons earlier. How are they different from steel?
Main difference is carbon content. Cast irons have significantly more carbon, typically between 2% and 4%. Steel is usually much lower than 2%.
And what does that extra carbon do?
It makes cast iron much easier to melt and pour into complex shapes using molds, hence the name cast iron. But that higher carbon also generally makes it more brittle than steel. It's less likely to bend and more likely to crack if you hit it hard.
So steel for things you might need to bend or shape or that need toughness, and cast iron for intricate shapes made by pouring.
That's a good general rule of thumb, yeah. Okay, so moving beyond iron, there's this whole universe of other metals, the non-ferrous ones. Chapter 4 looks at why they get used where they do.
Right, non-ferrous meaning no significant iron content. What are some key players here? Aluminum may be a big one.
Huge. We already talked about duralumin, but aluminum itself.
Right.
It's incredibly lightweight, naturally resists corrosion pretty well, conducts electricity okay, and it's relatively easy to shape and form.
So you see it everywhere.
Yeah.
Planes, cars, building trim, cans.
All of those, yeah. And it's interesting, we get aluminum both from mining bauxite ore, that's primary production, and also by recycling aluminum scrap, which is secondary production, and uses way less energy.
Good point about recycling. What about copper? We see copper wires everywhere.
Copper's big claim to fame is its fantastic electrical and thermal conductivity. It's just brilliant at moving electrons and heat. Plus, it resists corrosion well and is very ductile and malleable, easy to draw into wires or hammer into sheets.
Hence wiring, plumbing pipes, radiators, heat exchangers.
Exactly. And copper is the base for really important alloys, too, like brass, which is copper, and zinc and bronze, typically copper and tin.
Okay. What else is key in the non-ferrous world? Lead.
Lead's important, yeah. It's very dense, has a low melting point, resists corrosion well, and it's good at damping sound and vibration. So you find it in car batteries, radiation shielding, and solder.
Magnesium. I hear about that for lightweight things.
You got it. Magnesium is the lightest structural metal we commonly use. Great strength-to-weight ratio, machines easily. So aerospace, high-performance cars, laptop casings, phone bodies, places where minimizing weight is critical.
And zinc. I know it's used to coat steel.
That's probably its biggest use, galvanizing. Coating steel with zinc protects it from rusting. Zinc also has a relatively low melting point, so it's used in die casting to make intricate parts. And it's the other key ingredient in brass.
It's amazing how each one has its niche. The book mentions a whole slew of others, too, briefly.
It does, yeah. Just touches on things like beryllium, very stiff and light. Gallium melts in your hand. Hafnium for nuclear reactors. Indium in touchscreens and solders. Nickel crucial for stainless steels and those high-temperature superalloys and jet engines.
Huh.
Then you have the precious metals, gold, silver, platinum for corrosion resistance, conductivity, jewelry. The rare earths vital for magnets and motors, electronics. Refractory metals like tungsten, super high melting points for things like light bulb filaments.
Keep going.
Okay. Superalloys for extreme heat. Tin for coating cans and in solder. Titanium, fantastic strength to weight and corrosion resistance, used in aircraft and medical implants. Vanadium makes steel stronger. Zirconium, also used in nuclear applications. It's a huge palette of materials.
It really is. Just shows how tailored materials are for specific jobs. Now, we talked about the accidental heat treatment of duralumin. Let's circle back to intentionally messing with metal properties, Chapter 5, heat treatment of steel.
Right. Heat treating steel is all about carefully heating and cooling it to change its internal microstructure. And changing the structure changes the properties hardness, strength, toughness, etc.
So what are the main ways they do this?
The book outlines several key processes. There's annealing. This generally involves heating steel up, holding it there, and then cooling it slowly. The goal is usually to make it softer, easier to machine or form, and relieve internal stresses from manufacturing.
Okay, softening it. What else?
Normalizing. This is heating it up and then letting it cool in still air. It refines the grain structure, makes it more uniform, which often improves toughness and machinability compared to, say, an annealed state.
And then there's hardening, right, making it tougher.
Exactly. Hardening usually means heating the steel into a specific temperature range where its structure changes to something called austenite. Then you cool it really quickly, quench it, usually in water or oil.
And that rapid cooling does what?
It traps the carbon atoms and forces the austenite to transform into a very hard, strong, but often quite brittle structure called martensite.
Brittle isn't always good, though.
Usually not. So after hardening, you almost always do tempering. This involves reheating the hardened steel to a lower temperature, holding it for a bit, and then cooling it. This reduces the brittleness, makes it tougher, while still keeping a lot of the hardness and strength gained from quenching. It's a balancing act.
Okay, makes sense. What if you only want the surface to be hard? Like for gears or bearings?
Oh, that's case hardening. Techniques like carburizing or nitriding diffuse elements like carbon or nitrogen into just the surface layer of the steel at high temperature. Then you heat treat it so only the outer case becomes hard, while the inner core stays softer and tougher. Gives you wear resistance on the outside, but the part can still absorb shocks.
Clever. Now, the outline mentioned some diagrams. Iron-carbon phase diagram, cooling transformation diagram. Sounds complicated.
They are fundamental tools for metallurgists, yeah. The iron-carbon phase diagram is like a map. It shows you what structures or phases like ferrite, austenite, cementite are stable inside the steel at different temperatures and different carbon percentages. It tells you what to expect as you heat or cool.
Like a recipe chart for steel structures.
Kinda, yeah. And the cooling transformation diagrams, CCT or TTT diagrams, they add the element of time, or more accurately, cooling rate. They show how that high-temperature austenite transforms into different things, maybe perlite or bainite or that hard martensite, depending on how fast you cool it down.
Ah, so they help you choose whether to quench in water, fast, oil, medium, or air, slow, to get the structure you want.
Exactly. They're crucial for designing heat treatment cycles to get specific properties.
Fascinating. Okay, so that's steel. Do non-ferrous alloys get heat treated too? Chapter 6 talks about tailoring their properties.
Oh, absolutely. The principles are similar, use heat to change the microstructure, but the specifics, the temperatures, the resulting structures, they're different for each alloy system.
So like with the duralumin example.
Exactly. That precipitation hardening process solution treat, quench, then age is super important for many aluminum alloys to develop high strength.
What about other non-ferrous metals? Beryllium copper was mentioned.
Right. Beryllium copper alloys also rely heavily on precipitation hardening. Aging them after solution treating and quenching dramatically increases their hardness and strength. And like we touched on, they have that unique combination of high strength and being non-sparking, which is vital in some industries.
The non-sparking property is really interesting. What about common stuff like brass? Copper zinc alloys.
For brasses, annealing is a common heat treatment. Like with steel, it's used to soften the material, relieve stresses from cold working, and improve ductility so it can be formed more easily.
And titanium. That's a high-tech material.
Titanium alloys have their own complex heat treatments. Titanium can exist in different crystal structures, alpha and beta phases, depending on temperature and alloying elements. Heat treating allows metallurgists to control the amounts and arrangement of these phases to get specific combinations of strength, toughness, and fatigue resistance. Annealing is also used here.
So heat treatment is pretty much a universal tool for fine-tuning metals, ferrous or non-ferrous. Once you've got the material properties sorted, you need to shape it.
Yep.
Chapter 7, hot working versus cold working. What's the difference?
It all comes down to temperature relative to the metal's recrystallization temperature. That's the temperature above which deformed grains can reform into new, strain-free grains. Hot working is deforming the metal above this temperature. Cold working is deforming it below this temperature.
Okay, so hot working, is it easier? Like working warm plasticine?
Yeah. Generally, yes. It takes less force to deform the metal when it's hot. Common hot working processes are hot rolling, squeezing metal between rollers to make it thinner or give it a shape, like I-beams. Forging, shaping metal using hammers or presses. Extrusion, pushing metal through a die, like squeezing toothpaste from a tube to get complex shapes. Hot drawing, too.
And what does hot working do to the inside of the metal, the grains?
Because you're above the recrystallization temperature, the deformed grains are continuously being replaced by new, smaller, strain-free grains. This generally results in a refined grain structure and improves the metal's ductility and toughness.
Okay. And cold working? below that recrystallization temperature.
Right. So cold rolling, cold drawing, like making wire or tubes by pulling them through, dies, cold forging, bending, sheet metal, shearing, all done at lower temperatures, often room temperature.
And what does that do to the metal? Makes it stronger.
It does. When you cold work, the grains get distorted, elongated in the direction of working. You introduce a lot of those dislocations we talked about earlier, and they get tangled up. This makes it harder for them to move, which increases the metal's strength and hardness. We call it work hardening or strain hardening.
But there's a downside.
Yeah, the trade-off is usually reduced ductility. The metal becomes less formable, more brittle. If you cold work it too much, it can crack. Sometimes you have to anneal it between cold working steps to soften it again.
So hot working for shaping and refining grains, cold working for increasing strength, but you lose some ductility. Makes sense. How well do different non-ferrous metals handle this?
Chapter 7 touches on that too, their fabrication properties. Things like machinability, how easily you can cut them, formability, how easily you can bend or shape them, joinability, how well they weld or braze. Copper, for instance, is very formable. Aluminum machines well. These factors are critical for choosing a material.
Which brings us right to Chapter 8, fabricability of materials. Being able to actually make something out of the material is key.
Absolutely crucial. Doesn't matter how great the properties are on paper if you can't efficiently shape it and join it into the final product. This chapter gets into joining methods, especially welding.
Right, welding, sticking metal together with heat.
Essentially, yeah. There are many ways to do it. The book covers common ones like stick welding or SMAW, MIG welding or GMAW, which uses a continuous wire feed, TIG welding or GTAW, which is very precise, and resistant spot welding, like they use for car bodies.
They all sound kind of similar but different.
They use different ways to generate the intense heat needed to melt the metal locally and different ways to shield the molten metal from the air so it doesn't get contaminated. The choice depends on the metal, the thickness, the joint design, the required quality. Lots of factors.
Okay, and it's not just welding, right? There's brazing and soldering, too.
Correct. Brazing and soldering are joining processes that use a filler metal that melts at a lower temperature than the base metals you're joining. You heat the joint, melt the filler metal, and it flows into the gap by capillary action, bonding the pieces together when it solidifies.
What's the difference between brazing and soldering?
Temperature, mainly. Brazing happens at higher temperatures, above about 450 degrees C or 840 degrees Arum, and typically uses stronger filler metals, resulting in a stronger joint than soldering, which happens at lower temperatures. Think plumbing versus electronics.
Got it. Okay, so we've chosen our metal, treated it, shaped it, joined it. But sadly, things don't last forever.
Yeah.
Chapter 10, failure of metals under service conditions. This sounds important, but maybe a bit grim.
It's incredibly important for engineers to understand how things can fail so they can design to prevent it. The chapter covers common failure modes. First is just fracture breaking into pieces.
And there are different ways it can break.
Yes. A key distinction is between brittle fracture, which is sudden, catastrophic, with little warning or deformation, think shattering glass, and ductile fracture, where the metal stretches or necks down noticeably before it finally breaks. Think pulling taffy apart. You generally prefer ductile behavior because it gives warning.
Definitely want warnings. What else causes failures?
Fatigue failure is a huge one. This happens when a part is subjected to repeated stress cycles, loading and unloading over and over again. Even if the stress in each cycle is well below the metal's breaking strength, eventually a crack can start and grow until the part fails. Think bending a paper clip back and forth.
Ah, yeah, that makes sense. What about wear and tear?
Wear is another major category. It's the gradual removal of material from surfaces. There's adhesive wear surfaces sticking and tearing, sometimes called galling or seizing. Abrasive wear scratching or grinding by hard particles. Erosive wear impact by particles in a fluid stream. Gouging large-scale scraping. And fretting wear damage from tiny vibrations between contacting surfaces.
Wow, lots of ways for surfaces to degrade. And temperature. Does that cause specific failures?
It does. At high temperatures, metals can suffer from creep that's slow, continuous deformation under a constant load over time. Think of a turbine blade slowly stretching in a jet engine. There's also high-temperature fatigue and oxidation reacting with oxygen, basically high-temperature rusting or scaling.
And cold temperatures.
Cold temperatures can be tricky, too. Some metals that are perfectly ductile at room temperature can become brittle at low temperatures, making them much more likely to fracture suddenly if impacted. Think of the Titanic hitting the iceberg. The steel was likely more brittle in the cold water.
Okay, so a whole range of potential problems. And closely related to failure is Chapter 11, coping with corrosion, rust, and other forms.
Corrosion is basically the chemical or electrochemical attack of material by its environment. It's a massive cost globally. Think to rusty bridges, pipelines, cars.
How does it actually happen?
Often it's an electrochemical process, like a tiny battery forming on the metal surface.
Hmm.
The chapter describes different types. There's galvanic corrosion, which happens when you have two different metals connected in a corrosive environment. The less noble metal corrodes preferentially.
Like when you see rusty bolts on stainless steel?
Exactly. Then there's uniform corrosion, just general surface attack. Pitting corrosion, where you get small, deep holes. Crevice corrosion, which happens in tight gaps where the environment gets stagnant. Stress corrosion, cracking, a nasty combination where tensile stress and a specific corrosive environment cause cracks to grow. And densification, where zinc is selectively removed from brass alloys, leaving a weak, porous copper structure.
Sounds like metal is constantly under attack. How do we fight back? How do we prevent corrosion?
Several ways. First is smite material selection, choosing a metal or alloy that's inherently resistant to the environment it will be in. Using things like the galvanic series helps here.
Okay, choose the right stuff.
What else? Protective coatings are huge. Paint is the obvious one, but also metallic coatings like galvanizing, zinc on steel, or chrome plating. Anodizing creates a protective oxide layer on aluminum. You can also add corrosion inhibitors to the environment, chemicals that slow down the reaction.
And I've heard of cathodic protection.
Yes, that's an electrochemical method. You basically force the metal you want to protect to become the cathode, the non-corroding electrode, in the corrosion cell. You can do this either by connecting it to a more reactive metal, a sacrificial anode like zinc or magnesium, which corrodes instead, or you can use an external power source to impress a current onto the structure. Very common for pipelines and ship hulls.
So a whole toolkit for fighting corrosion. It really feels like we've covered a huge amount of ground here, from that accidental duralumin to the details of preventing rust.
We really have. This handbook, Metallurgy for the Non-Metallurgist, it just opens up this whole hidden world.
The big takeaway for me is just how interconnected everything is.
Yeah.
You know, the alloy mix, how you heat it, how you shape it. It all links directly to how it performs, how it fails, how it corrodes.
Absolutely. It's all about controlling that internal structure to get the properties you need for the job.
And that duralumin story, the surprising fact that a weekend off led to such a breakthrough, it really sticks with you. It shows that science isn't always this perfectly planned path.
Definitely not. Serendipity plays a big role. And hopefully for you listening, this gives you a bit more appreciation for the incredible material science that's literally all around you.
Yeah, from your phone to bridges to airplanes.
Yeah,
It's all underpinned by this understanding of metals.
it truly is.
So maybe a final thought to leave you with. As we push for materials that are even stronger, lighter, maybe more environmentally friendly, how will metallurgy adapt?
Yeah.
What kinds of new alloys or processes are out there just waiting for their own accidental or maybe intentional discovery to change things all over again?
That's the exciting part, isn't it? What's next in the world of materials? It's constantly evolving.